Welcome back to Honors Calculus. In this video, we're going to be talking about set theory and sets of numbers. Set theory is a very nice place to start in most undergraduate mathematics courses because it gives a nice solid foundation on which just about anything you might want to do in undergraduate mathematics can eventually be derived. You should already be familiar with many of the basic ideas of set theory. Let me go ahead and start writing down a couple of definitions. And perhaps getting my head out of the way would be a good idea here. A set is a collection of objects which we call the elements of the set. If we have a set that we call A, and we have some element of that set that we'll call X here, we can say that X is an element of set A in symbols using this kind of E-looking thing. I tend to think of it as the letter C with an extra line in the middle rather than thinking of it as an E. Um, but it's the contained within or element of operation. Uh, and really the one thing that we can do with sets, because sets are incredibly generic. There is almost nothing about a set. A set is a bag. And the only thing you can say about a bag is that there's stuff in the bag. But amazingly, with just that, we can build up some really powerful ideas in mathematics. I'm going to try to keep a convention that if I'm talking about a set, I'm using capital letters, and if I'm talking about an element of the set, I'm using lowercase letters. So let's let A and B be sets. And in this definition, I've used a bunch of abbreviations and symbols. In theory, you've seen all of these before. In practice, 50-50. But very commonly in mathematics, we use this abbreviation IFF, which means if and only if, or a nice shorthand. If-then statements can be a little bit tricky at times. If it is raining, then I will want my umbrella. It's entirely possible that I'll want my umbrella for other things. I will want my umbrella if and only if it is raining. I want my umbrella on rainy days, and I only want my umbrella on rainy days. If it's not raining, I don't want my umbrella. A subtle difference, but subtle differences in logic are what mathematics is all about. And then we've got this upside down A symbol. We read that symbol as for all or for every, or for each. Right? So let A and B be sets. We say that B is a subset of A, and I just realized I forgot to write down the notation for that, but we say that B is a subset of A if and only if for each element X in B, that element X is also in A. Right? So understanding how to look at these symbols and read them in spoken language is in and of itself an important part of this lesson. If and only if for each element X in B, that X is also an element of A. Several different ways you could approach that, but the context, the meaning should be the same and should start to become apparent to you. We denote that B is a subset of A using this symbol. It's a C with a line underneath it instead of a line in the middle. The line underneath tells you that we are dealing with um, two sets rather than an element of a set. And that is something that we have to pay attention to. It's not really going to come up in this course, but it's entirely possible to have a set which has sets in it. Again, if you think of a set as being a bag, you can take a large bag and you can try to better organize the things in that bag by putting a couple of smaller bags inside. When you've studied set theory in the past, you may have dealt with this idea of a proper set and a not proper subset. Um, the problem with this definition is that for any set A is a subset of itself. And you can see here that I have labeled this statement THM, which is an abbreviation for the word theorem. A theorem in mathematics is something that we need to validate. It is not just an assumption about the world. It is something that we claim must be true based on what we have already established. All we have established right now is the definition of an element and the definition of a subset. But that just means the proof is going to be easier. All right, so after every theorem comes a proof. And I often abbreviate proof as PF because, again, mathematician, incredibly lazy, and writing out the whole word proof is just entirely too much work. So looking at our definition of a subset, the definition talks about elements. So let's find a random set called A, and let's find an element of that set. And so the definition of a subset, if I scroll back up, says that for any element of the subset, that thing is an element of the original set. So consider any element of set A. By definition, that thing is also an element of set A. And that's what it takes to say that something is a subset. Early proofs in any mathematics course tend to be kind of a little bit counterintuitive because they are so straightforward, and this is definitely among the list. For many of you, this is your first real-time thinking about proofs in an organized sense, and if so, this is probably not the best one to start off with, but it is very emblematic of the idea of a proof. We have a definition. We look at that definition, we figure out what we know about that definition, and we try to see if we can state that. And if we can, then we have a proof. And as soon as we reach the conclusion that the theorem says we are going to reach, we want to close the proof with what's known as a QED tombstone symbol. Some people draw a square, some people draw a square and fill it in. Some people literally write out the letters QED. I've seen other symbols as well. But some sort of end of proof symbol to say, hey, we've just finished a proof. And that's important because now I can say that, okay, I'm done talking about the proof. I'm going back to my discussion, my definitions, everything that I've been doing. The empty set is denoted and defined. Denoted as a circle with a slash through it. Defined as a set that has nothing in it. Hence the name. The empty set is the set that contains nothing. And that takes us to the single weirdest bit of logic in mathematics. For any set A, the empty set is a subset of A. And the general idea that we are using here is something known as a vacuously true statement. A vacuously true statement is a statement that is true because there's nothing that we're actually talking about, right? By definition, for the empty set to be a subset of A, we want to show All right, so we want to show WTS. And the definition said, for all elements of the subset, which in this case is the empty set, that thing is in set A. Since the empty set has no elements, then that means that there are no elements of the empty set which are not also elements of A. Put a little bit more concretely to our situation, that means that there is no way for this statement to be false. And that's the entire idea of vacuously true. Because we are talking nonsense, we are talking about a thing that doesn't exist. There is no way for that thing that doesn't exist to ever not do what we tell it to do, or to ever do something other than what we tell it to, because there's no way for it to do anything. So there's no way for this statement to be false. And so by process of elimination, it is true. That's goofy. If that doesn't make sense to you right now, that's okay. This idea of a vacuously true statement doesn't come up all that much in any one mathematics course throughout all of the mathematics courses that you will take as an undergraduate, no matter what your major. Math majors, physics majors, engineering majors, computer science majors. The idea of a vacuously true statement will probably come up once or twice in every undergraduate math course you take. And considering the number of things that are going to come up in an undergraduate math course, that's really not a lot of things. So if it doesn't quite make sense to you why this proof holds true, that's okay. The important thing is the statement of the theorem itself. In order for set theory to work, we have to accept that the empty set is a subset of every set. And we have to accept that every set is a subset of itself. Those are the foundational ideas of set theory, and we're able to build off of them in surprisingly useful ways. Now that we've done all of the abstract work, it's time to start looking at some things a little bit more concretely. Oops, sorry about that. So there are a couple of sets of numbers that you should be familiar with already. You may or may not be familiar with the notation for them, but you should be familiar with the name of the natural numbers, which are sometimes also known as the counting numbers. And I think it's pretty easy to define the natural numbers by the numbers you count with, 1, 2, 3, 4, 5, and so on. The interesting thing here is this symbol that I'm using to represent them. It kind of looks like the letter N with an extra line in it. And we call a symbol of that sort a blackboard bold symbol. And all of the major sets of numbers that we're going to be talking about have a blackboard bold symbol that we use to represent them. The integers use the blackboard bold letter Z, which doesn't make sense at first glance, but there is a reason for it. My German pronunciation is terrible, so I'm not going to try, but the German word for number starts with the letter Z, and that's why the integers use the blackboard bold Z symbol. I guess also in that is that German mathematicians were the ones who were really starting to establish the ideas of set theory when the formal foundations of mathematics were being developed. So the German language word for number starts with Z, and that's why that Z symbol is what we use for the integers. And the integers are the positive or negative numbers. So instead of going off forever in one direction, it goes off forever in both directions. But listing out all of the elements like that seems to be pretty reasonable. Right. Up next is the rational numbers. And for the rational numbers, we use the blackboard bold Q, which is the same root word or a language conjugate to the word quotient. Rational numbers are fractions, quotients of two numbers. And in order to talk about the set of rational numbers, this is usually when you first get introduced to a thing called set builder notation. All right, the rational numbers are the set of all things that can be written as P over Q, such that P is an integer and Q is an element of the set of natural numbers. Right, so if you've never seen set builder notation before, the way we read this is the set of all, or to be more formal, the set of all elements which can be written as P over Q, such that P is in the integers and Q is in the natural numbers. So P can be positive, negative, or zero. Q can be positive only. There's ways of establishing things a little bit differently, but that seems to be the most straightforward way of dealing with this. And a quick theorem, I'm not going to take the time to actually write this proof out, but it is a theorem, so it should be something that you prove. The natural numbers are a subset of the integers, and the integers are a subset of the rational numbers. Right? The natural numbers and integers, I think, is pretty straightforward. To get from the integers to the rational numbers, think about the fact that little q could be equal to 1, and anything divided by 1 is that thing. All right, so I'm not going to write that proof out, but that's something I wanted you to at least see, at least think about. You have almost certainly been shown these three sets of numbers at some point in the past. And generally, in most algebra courses, the next thing that is discussed is, and then there are numbers like pi and the square root of 2, which can't be written as a fraction, and we call those things the real numbers. And you never write down a set notation for the real numbers. That's not satisfying at this point in your education. I hope you agree that that's a very hand-wavy result and not very interesting. In this course, I want to be able to deal with the set of real numbers and the properties of the set of real numbers. In the next few lessons, I'm going to start establishing some of those properties and allow us to get through and see how the real numbers work and how to define the real numbers as a set. But for right now, just to get a better idea of some of the tools that you can do working with sets, I'm going to stick with just these three sets, the natural numbers, the integers, and the rational numbers, and we'll think about these sets of numbers, and actually specifically just the integers, so that we can get used to some of the properties of sets, and we can get used to some of the ideas around writing proofs. Right? So one thing that we haven't looked at is how to establish equality of sets. We say that two sets are equal if and only if each of those sets is a subset of the other one. That's kind of an odd way of defining set equality, but it is very nice because it allows us to have a rote tool for establishing that two sets are equal when there are too many elements in the set to really establish the entire roster. For any relationship that we call equality, there are going to be three properties that hold true. The reflexive property, anything is equal to itself. The symmetric property, it doesn't matter what order you state the equivalence. If A is equal to B, then B is equal to A. And the transitive property, that's the juggle three things rule. If A is equal to B and B is equal to C, then by substitution, A is equal to C as well. We should prove that this definition of equality actually satisfies all of those properties so that we can be happy with it. But for the sake of time, I'm not going to do that in this course. For anyone who is moving on to eventually take a course in discrete math, in that course, we look at these properties and we prove that this definition of set equality actually satisfies them, because properties of equality is a big thing in discrete math. It's not that big of a thing in calculus. Instead, I want to use this definition of set equality to consider a couple of sets. I'm writing this backwards, sorry about that. So let's consider two sets here. Set A is the set of all numbers which can be written as 5k plus 3 for some k in the integers. And set B is the set of all numbers that can be written as 5k minus 2 for some k in the integers. Clearly, the definitions of these two sets look different, although they don't look drastically different. And I claim that these two sets are in fact equal to each other, and I'm tasking us to prove that fact. All right, so if we're going to prove something, we're going to start off by saying this is a proof, and we'll start writing down what it takes. All right, the definition of a set, or of set equality that I put on the previous screen says we need A to be a subset of B, and we need B to be a subset of A. All right, so step one, we want to show that A is a subset of B. What does it mean to be a subset? Well, pick some element of the set that is a subset and show that it is an element of the larger set as well. All right, one more abbreviation that I don't think I've used yet today. ST is the shorthand for the phrase such that. Once again, a phrase that we use very frequently in math, and mathematicians are inherently lazy, and writing out the whole phrase such that is just too much work. So, WTS wanted to show. ST such that. We use these abbreviations all the time to save ourselves a little bit of writing. And one of the things that is the most important to learn in a college math course is how to get past all of those abbreviations and actually write things down. All right, so we established that x is equal to 5k plus 3. And our goal here is to show that x is an element of set B, which means it has to be written as 5k minus 2. Right. Now, the one thing to pay attention to here, the one thing that's going to make this a bit of a challenge, is this letter k and that letter k does not have to be the same number. We're talking about some number, right? Our variable is a placeholder. And because we're using that variable in two completely different situations, if any of you have studied computer programming, you may know the difference between a local variable and a global variable. That's exactly what's happening here. K is local to the definition of set A, and K is local to the definition of set B. They are not global variables. They don't have to mean the same thing. But they are placeholders. So it still tells us that we want to be able to write 5 times k plus 3 as 5 times some integer minus 2. Well, how do you get from plus 3 to minus 2? Very conveniently, the answer is to subtract 5. Right? But I can't just arbitrarily subtract 5. So I'm going to use mathematicians' favorite trick. Take something that is pretty simple and make it much more complicated by either multiplying and dividing by the same thing. That's a trick that you learned in basic arithmetic classes on dealing with fractions, or adding and subtracting the same thing. What would happen if I add 5 and immediately subtract 5? Absolutely nothing, right? This is the exact same number we had before. It just went from looking fairly nice to looking quite a bit more complicated. Now, from the first two terms, I'm going to factor out the common factor of 5, leaving behind k plus 1. From the last two terms, I'm going to simply simplify. Minus 5 plus 3 is minus 2. And then I'm going to notice that if k is some integer, if you take an integer and you add 1 to it, you get another integer. And just to make it really clear, let's introduce a new name for that. Let's call it L. And that thing is also an integer. So now we have written x as 5 times some integer minus 2, which is exactly the definition of set B at the top of the screen. So x is in set B by definition. And then I get to do mathematician's favorite argument. Named a couple of things as mathematician's favorite, right? Mathematician's favorite algebra tool, mathematician's favorite logical argument. Similarly, we just did something and we can go and do almost the exact same thing again, and I'm being lazy, so I'm not going to write it out for you. That's what similarly means, and you see it all the time in mathematical writing. I'll come back to that in just a few moments. But we can go through an incredibly similar argument. We can choose some new element y, set it as an element of set B. We can show that that element y is also in set A, and we can conclude that B is also a subset of A. Part 3 of the proof. We saw that A is a subset of B and that B is a subset of A. And so by definition, set A and set B must be equal to each other. And that closes off that proof. As I wrap up here today, I want to draw your attention back to that really annoying similarly argument that I made. That's your assignment. I would like you to take some time, look through the argument of part one, and write out the similar argument for step two here, and see what you can do with that. With that, I'm going to wrap up our discussion of this topic. Thank you for joining me, and I'll see you in the next video.